Hello. Today I'm going to talk about black holes in this lecture. And what we see here is artist's representation of a black hole, or really what you see is the material around the black hole being in the center. And it's just this material that's swirling around the black hole, some of it eventually going into the black hole. All right, so let's take a look here. When massive stars reach the end of their life cycle, they collapse under their own gravity. Now, our star is going to do the same thing, but it won't become a black hole. It's not big enough. The largest of these stars crush down into a black hole. Now, it shows three different end stages for stars here. White dwarf star, which is what our sun will eventually collapse down to. This is about the size of Earth. Neutron star, which is about the size of New York, is the next smaller stage. And then for the smallest stage are the black holes. Also, they vary in size, but we'll just say about the size of New York City. If gravity is strong enough, the atoms of white dwarfs get squeezed down into a neutron star. If a neutron star is massive enough, it crushes neutrons together into a black hole. So at each stage, they take whatever atoms or subatomic particles there are and just keep squeezing them all together. Okay, so what we have here, we have to talk for talking about black holes, we have to talk about space-time. And the image up here is a representation of space-time. Space-time can curve, and we don't think about this because we don't see it in our normal lives. But this has been proven time and time again. Normal space-time is warped and bent by gravity. And that's what we see in the second image, right? There is a mass, a weight here, and that actually bends space-time around it. A straight line in curved space-time does not look like a normal straight line. So this ant is walking a straight path here, but the ant is also walking a straight path right here. It's not walking a path where it turns and it changes direction. It's space-time that curves. So the ant is walking in a straight line the whole time. Okay, now down here, what we have are some more examples of curved space-time where you have a big mass in the center, like some galaxies, and a galaxy behind Earth, or behind this mass. From Earth, we can see that the light from this distant galaxy gets curved around other large masses, okay? Light that passes through curved space-time is still going in a straight line. It's not actually the light path that changes direction, but the space-time geometry. I'm sorry, but the geometry of space-time, geometry. And if this is a little confusing at first, don't worry. It takes a while to start trying to wrap your head around this. Not an easy concept. Okay, so we got a couple depictions here. We've got the sun and how our sun curves space-time, and then a very concentrated mass of a white dwarf curving space-time. Even more so a neutron star, which is an even higher concentration of mass curving space-time. And then ultimately you'll get a black hole, which curves it so much, we say it goes to singularity or infinity. The warping of space-time from a black hole is infinite, disappearing into singularity. That means anything that drops below the event horizon will not have a path out of the black hole. Space-time is warped too much. So here's the event horizon, and they're saying if you go below this event horizon, there is no actual space-time path to get out of that. There's no direction you can go to get back out of that event horizon, because it's warped so much. And then down here, to wrap it up, we see some clocks, and what you'll see is, let's see here. You see an outside observer, and their clock is moving forward, right, at a certain pace. But then if you compare the clocks of something falling into the black hole, you'll see that it's hardly moving at all. It's very slow compared to these clocks. Space-time is both our concepts of space and time wrapped together. That means gravity also affects time, slowing down near high gravity. So the closer something gets to a high gravity source, the more time slows down for them. The further away you are, the more time speeds up, because space and time are one thing. All right, thank you very much.